Okay, let me share my screen. Welcome back. So last time we were discussing simulation of the Ising model with classical Monte Carlo. I was explaining the simulation, this simple Python routine. So let me restart the kernel and restart and clear output. Let me do this so that we start from fresh. Simple Python. Okay, so I wanted to explain this routine, and I quickly try to explain this, but let me try to do it more carefully this time. So at the very beginning, we usually select this configuration of the spins to be completely random, which corresponds to very high temperature, and we have to at the beginning calculate what is the current energy with which we start. So because this lattice is an input to this routine and can be any lattice configuration, so we need a starting energy, and then later on we're going to only update the energy. Isn't that we're never going to anymore calculate the entire total energy. We're going to only update the total energy, but at the beginning we have to calculate it from scratch. Okay, so magnetization, we calculate it from scratch at the beginning, but that's really easy because magnetization is basically just the sum over all lattice points of either +1 or -1, which in this case in Python we could just write as a sum of this lattice. And then, of course, we know that the number of lattice size, well, the size of the lattice is n times n. So therefore, n is length of the lattice. Here I added one more variable, which is different than what is in your notebook. I just modified it now, and you can modify as well if you want to follow. So you can add this n accept is equal to 0 here, and this will actually count accepted steps. Now, why did I do that? Because I argued last time that it's not necessary to measure every step, but we can measure only from time to time. And a good rule of thumb is to measure as often as we typically make a change. So let's not overdo, let's not measure too much, let's not spend too much time in measuring if the configuration almost never changes. So in order to prove to you that this acceptance rate is not so high, I'm going to now check how often do we accept the step. So therefore, I will set this n accept to 0 at the beginning. And then here n1 will count how many measurements did we actually make altogether. And now E1 is going to be the average energy, M1 is going to be the average magnetization, E2 is going to be square of the average energy, and M2 is going to be square of the average magnetization. Now clearly this N2 is N square, and then this loop is the entire simulation loop. So what do we do at each step? So this first two lines select randomly a lattice site which has index I and j. So in this case we do this with just generating from one random number of the size n square. Then we take modulus and divide by n. We could just equally well select this lattice site I and j independently with two random numbers between 0 and n, rather than from one random number between 0 and n square. So, but the point is we have now randomly selected a site which we want to flip. So the idea is we have a random site which we want to flip. We look at the spin at that site, and then we also look at the Weiss field for that spin. And Weiss field for the spin, as we discussed, is basically the neighbors. So the left neighbor, the right neighbor, the upper neighbor, and the lower neighbor. Unfortunately, I just realized that I don't see you. So something similar that happened to me as the last time. I don't see the participants, which is a little strange. Oops. More hide video panel, and then show video panel, but I still don't see you. Hide floating meeting controls. Oops, this is not good. Yeah, I think I have similar problems that I had some days ago. I guess you see okay, huh? You see my screen, my screen share. Now you don't, huh? Share screen, yeah. Now you don't, yes. So unfortunately, somehow the video panel of you, of all the participants has disappeared. I guess this is a bug in Zoom, but okay, I will survive without that for now. Okay, so sorry, I was explaining that yeah. So this Weiss field looks at all the neighbors. So the left neighbor, the right neighbor, the neighbor above, neighbor below, and sums them up. And then we know that the energy of the energy that corresponds to spin flip on this side, energy change, is equal to 2J times Weiss field times S. Basically, J is set to 1, therefore it's 2 Weiss field times S. And then, according to Boltzmann, we are supposed to accept the step with probability e to the minus this change of energy divided by t. And we do this by pre-computing these exponents. And therefore, our job is now very easy. We just take the exponents from the right table, from the right place in the table. So PW has this exponents pre-computed, and therefore this probability, which is e to the minus, so this probability is supposed to be e to the minus delta E divided by t, is very easy to compute. Is 4 plus this Weiss field times the spin. So now if this P, of course, can be either bigger than 1 or smaller than 1, because these P exponents can be exponents of a positive number. But of course, if P is bigger than 1, we were always going to accept the step when we do this thing. And if P is less than 1, we are going to accept the step sometimes and sometimes not, with probability which is proportional, which is equal to P, isn't it? When P is less than 1. And so that's the statement to write. So random rand is a uniformly distributed number between 0 and 1, and we accept then the step with this probability which is equal to P. This is the Metropolis acceptance probability, isn't it? So now if this step is accepted, then what do we need to do? Well, we flip the spin on this lattice side. We have to update the energy. So here above, we calculated initial energy only, initial energy. And now later on, when we accept the step, in principle, we could just pre-compute the energy. We could compute energy again on this new lattice, because we changed the lattice, one spin on the lattice, and we could use this C energy here and compute the total energy again. But of course, that would be way more expensive than what needs to be done, because we know that the change of the energy is local, is very small, is basically just this delta E that we computed before. So therefore, we can just update energy with this delta E, which is 2S times Weiss field. And magnetization, we know, again, we could compute it by doing the sum over all lattice sides, but we don't need to do that, because we know that the sum over all lattice sides has to be the same as magnetization before, minus 2S. So basically, we just update energy and we update magnetization. We don't need to compute from scratch. And at the same time, we're adding this n except plus equal 1. So this line is new, is different than what you have in your notebook that you downloaded from the internet. So again, why I'm doing this? Because I want to show you how often do we accept the step. So when we return here, we're gonna return n accept divided by all iterations that we've done, doesn't it? So n accept measures the steps that were actually accepted, and of course n ITT is number of all iterations or number of all steps that we were trying or we contemplated, and therefore this gives you acceptance step probability. And the question is, of course, how big is this acceptance step probability? Is it 50%, 20%, 100%? What is it? And of course, this acceptance step probability somehow is kind of related of how often do we measure. So because this statement here, as we discussed last time, is measurement and has to be done in the same level as the trial step, when we try the step, because each step counts. Each step in Monte Carlo simulation is a step, even if the step is rejected. And then we measure only after warm-up period is over. So in other words, if this iteration is bigger than some number of warm-up steps, which we're going to set to a few thousand, then we start measuring. Otherwise, we throw away this period when we are still not equilibrated at the desired temperature. So of course, this warm-up step needs to be larger when we start from very, very bad configuration. But if we slowly change the temperature, like we're going to do down there, we're going to change the temperature just a little bit, then the warm-up steps don't need to be so large, because the temperature has changed only a little bit, and therefore the configuration that we have is most likely pretty close to the configuration at this particular temperature. Okay, so now here is the statement that says, don't measure every time, measure only every measure steps. Okay, so only from time to time, isn't it? If measure is 5, then this will be true only every 5th step, isn't it? So what do we do when we measure? Well, we update this counter N1, which counts how many times we measured things. Then we update energy. We add to the sum of the energy, this current energy, sum of the magnetization, the current magnetization. So clearly, if we divide now E1 and M1 by N1, we were going to get average energy and average magnetization. And that's what we returned. That's what we do here. Yeah. So this step here, you see, calculates the average energy and the average magnetization, because this is how well, here we have just a sum of energies, here we have sum of magnetizations, but at the end we calculate the average. So this would give you the average energy over the simulation, of course, and the average magnetization over the simulation. Okay, so in addition to this, we also have the energy square and the magnetization square. Okay, so which we know it's needed for specific heat and for magnetic susceptibility, to calculate magnetic susceptibility. So now that we have here, we could also calculate, of course, E square average and M square average, but somehow I decided to do this when we calculate specific heat. Maybe it's more clear if we do this. E2 average and M2 average is equal to E2 divided by N1 and M2 divided by N1, for example. So now this is average energy, average magnetization, average of the square and of energy and square of magnetization. And now I can substitute this E2A, M2A. Okay, so now you see that specific heat basically is the E square energy, well, it's the average of the energy square minus square of the average, isn't it? And this again is average of the magnetization square minus magnetization square average, isn't it? So the symbolically, that's how you write. So this is kind of fluctuation of the energy and fluctuations of the magnetization. So specific heat, of course, is well known to be fluctuation of the energy, and susceptibility is fluctuation of the magnetization. Okay, and clearly these two things are non-zero. Why? Because, well, because the system fluctuates at particular energies. That once we are in the ground state, of course, then fluctuation ceases to exist, and then fluctuation goes to zero. But here we actually divide fluctuation by the t square, and that's still finite even at t is equal to zero. Okay, so now what we return is then the magnetization per lattice site, energy per lattice site, specific heat per lattice site, chi per lattice site, and probability that we accept the step. Okay, so again, in the very last step before we return, we calculate all the quantities per lattice site for convenience, because otherwise the values would increase when we increase the lattice site, the number of lattice sites. Okay, so now let me try to rerun this. Now we are gonna simulate now this routine for just one temperature. The temperature in this case is gonna be this. Yeah, I modified this from 2 to 2.269. So the reason that I'm going to start with temperature of 2.269 is because if we go to this Ising model simulation, you will see that these guys actually give us nicely the critical temperature, which is 2.2691 something. Okay, so we know that Ising model has critical temperature around 2.269. So we're going to start here with the exactly critical temperature. Why is that a good idea? Well, kind of this temperature is the most important temperature where we want to reduce the fluctuation, have the best precision. Okay, so see this, I've done now only this temperature. We get average magnetization, some number, which we know that fluctuations close to the transition temperature are very, very large. So this magnetization sometimes is going to be large number, sometimes it's going to be small number. So don't trust this too much. However, specific heat should be pretty large, close to the transition temperature. But the important point, what I wanted to show you here, is the acceptance step is of the order of 20%. So therefore, since the acceptance step is the order of 20%, then measurement should be of the order of 5. So basically, it's a good idea to measure only after every 5th step. So that's the reason why I use this measure is 5. So there is no point of measuring every step. If I set measure is equal to 1, I will measure every step, but there is no point because on average, close to the transition temperature, I'm accepting only 20% every 5th step only, so only 20% of the attempted steps. Yeah, of course, the warm-up period here is short. The number of iterations is actually 1, 2, 3, 4, 5, 6, so it's 5 million. Okay, so this was just for one temperature. Now we can do the thermodynamics for all temperatures and get some physical plot, something that kind of gives you some physical intuition about what's going on in the model. That for us is most important. So how do we do that? Well, for this we are gonna create some mesh of temperatures, and the idea is to start first with very high temperature, way above the transition temperature, and then slowly changing the temperature through the transition temperature. So the choice is to start at temperature 5 and going down to temperature 1/2, and we're going to have 30 points. Of course, we could have more points right now, but since we are making only 5 million steps every time, This is not going to be terribly precise, so there is no point of having very large number of points, since the precision of these points is not so great either. Okay, so the warm-up steps is going to be only 1,000, and I justified this before that we don't need very large warm-up time. We could reduce this number even further because we are making relatively small steps of 1/2. So therefore, we are in temperature. So therefore, our previous configuration is a good approximation for next step. And of course, measurement is going to be only every 5th step. The lattice height is going to be 20 now. I warn you that if you increase this dimension of number of spins, instead of 20, you would put in 100, then you would need to increase substantially number of iterations, because otherwise the plot will not make any sense. Just the phase space becomes so much bigger if n is large that you need to increase number of iterations. Okay, so now what do we do is very simple. We first pre-compute the exponents that correspond to this particular temperature. Whenever temperature is changed, of course, here is loop over temperature. So when temperature is changed, we pre-compute the exponents. Then we run the simulation at that temperature with those exponents, PW. The rest is kind of obvious. We give the current lattice heights and so on. So you see this lattice here is not being, how can I say, in this loop here, we always take the lattice configuration from previous temperature, because that allows us to have relatively small warm-up time. So this warm-up time is small because the lattice in the next temperature is going to be the one from the previous temperature, which was equilibrated to the previous temperature. Okay. Yeah, and what has been returned is this magnetization energy CV specific heat, but here I'm also returning this probability to accept something that that I modified right now today, and you don't have this p accept in your notebook. So if you're following before and you're updating this simple Python in such a way that you return p accept, then you also need to update this point here that simple Python returns p accept in addition to other quantities. Okay, so what we also do here in this step is that we kind of remember magnetization, energy specific heat, and suitability at this energy, and we print out the information, and then we're going to plot the final results. So let me run this. So you see this code is relatively fast. So we have 30 steps already done between 5 and 0.5, and as we see at the transition temperature around 2.2 here, the acceptance steps, the acceptance probability is of the order of 20%, as we saw before. Of course, when temperature is very low, then the acceptance rate is also very, very small. So in the sense, we see that the low temperature are kind of hard to simulate, but on the other hand, they're pretty boring because the magnetization doesn't change anymore. So basically, we're close to the ground state. So at high temperature, of course, the acceptance rate is much higher. But on the other hand, this high temperature problem is relatively trivial in the sense that we are very close to completely random configuration. So the thermodynamic quantities are very, very easy to compute anyway. Okay, so now that we have all those quantities, energy, specific heat, magnetization, and so on, we can plot all of those simply with usual matplotlib. And we have here the curves. So let me try to explain what we see. So the total energy at high temperature is close to zero. Of course, at very, very large temperature is supposed to be zero. And then at the transition, which is around 2.2 something, energy goes close to -2. So we know that the ground state energy has to be -2 times the number of lattice sites, isn't it? So therefore, this final configuration, we know that is the one where all the spins are either pointing up or all the spins are pointing down, doesn't it? So how do we know that? Because, each spin has what, 4 neighbors. So this would be 4. Energy would be -4, but then we count each pair twice. So basically, it's only -2. Yeah, so this is for energy. What about specific heat? Well, fluctuation of the energy is the largest at the transition temperature. So therefore, we know the specific heat has to be peaked at transition temperature, and it's somewhat larger, about TC, and it basically here it vanishes vanishes pretty quickly when the temperature goes to 0. So magnetization, on the other hand, is kind of obvious. So magnetization is 0 above transition temperature. Now here we have lots of fluctuations. So unfortunately, close to transition temperature, this precision of the magnetization is pretty bad. I mean, its precision of specific heat is also pretty bad, but of magnetization is also very, very poor. And of course, at low temperature, magnetization is 1. It could be -1 or +1. So if we simulate this, thing again, I have to simulate. If we simulate this thing again, we might get magnetization to be opposite, -1. Of course, depending on the random seed. Let me see. No, it's still positive, but it could be that when you run, that's going to go to -1, which means that all spins point in the same direction. Now, however, here close to the TC, we know that magnetization should go as a square root of magnetization, square root of temperature, isn't it? So here, the rise of magnetization should be proportional to the square root of magnetization, basically it should go as T minus TC to the power of critical exponent, and critical exponents, of course, for the Ising model are known. As far as I remember, it's 1/2, but actually I have to check if it's exactly 1/2. Maybe it's not. The mean field is 1/2, and the Ising model, I think, has an exponent which is similar to that, or maybe the same. Okay, so specific heat is plotted in a separate plot, and the reason for this is because specific heat diverges even faster. Now, we know that the specific heat should diverge as 1 divided by T minus Tc, as that. So basically, this curve in the infinite system, of course, is 1 divided by T minus Tc on about the critical temperature, and below it also diverges with this, I think, with the same exponent, but the prefactor is smaller. So therefore, it looks like the specific heat is very small below Tc. But I mean, if we zoom in this, we will see that it's not exactly 0. It's actually also goes as 1 divided by T minus Tc, but with much different, smaller prefactor. Okay, so that's what is the physics of this model. Now, the trouble is that while this simulation is relatively very straightforward to code, and I'm sure that some of you have already done this simulation before, it's very hard to get quantities very close to transition temperature. So, or basically very precisely close to the transition temperature, where things are most important, where the physics is most interesting. So, so-called critical phenomena is hard to get from this. We need very large, very long temperatures, and of course we also need to increase the system size to remove the finite size effect. So basically, get to the thermodynamic limit, and so the brute force is actually quite. With brute force, it's very hard to access large sizes, and and precise simulations. So therefore, people invented all kinds of interesting improvements of the algorithm. And the first thing that I want to make you aware of is so-called cluster algorithms. Now, we already saw this cluster algorithms in this Ising simulation here. So let me remind you that here we can run what they call Metropolis, which is what we implemented right now. We didn't implement this simulation, which would show which would plot the lattice configuration, but we calculated thermodynamic quantities rather than displaying that. Of course, we could also display if we wanted to, but now I wanted to point out that there is something here that's called Wolff's algorithm. Okay, and when you look at it, you see that this algorithm is actually quite different, isn't it? It doesn't flip one spin, but somehow it makes much more changes at every step, doesn't it? So what does it do? Well, it actually more or less flips a domain. So what's domain? Well, domain is whatever you see has the same color. So there are kind of spots which have the same color, and this is what we can call domain. And so the first approximation, what this algorithm does is it flips the entire domain, okay, or almost the entire domain. So why is that a good idea? Well, because this turns out to be very, very efficient near the transition temperature and below the transition temperature. So this is now, we are close to the transition temperature. We see that the changes now occur globally. We call it global update because the changes clearly doesn't occur only in a very, very limited area. So Metropolis, of course, you see things change very, very slowly. You see the same pattern for a very, very long time. And it's hard to get out of this pattern. While with Wolff's algorithm, the changes are much more faster. And you see that the configuration kind of changes pretty quickly. And the pattern that we see after a few seconds is quite different from previous one, which shows you that that with this we avoid critical slowing down. We avoid the problem that let's say close to the transition temperature, we are kind of almost stuck to some local configuration, to some configurations, so that we are not visiting the entire phase space quickly enough. Okay, so yeah, when we of course reduce the temperature, then this algorithm is even more efficient. You see that when we are below the transition temperature 1.3, the system knows immediately that we are ordered, and immediately it puts all spins either up or down. While, as you remember, when we have this Metropolis algorithm, oops, it's hard to switch right now. We have Metropolis algorithm, and we go through TC. We have this problem that sometimes, yeah, we have this pattern of those domain walls, which are very hard to get rid of. Of course, Wolff's algorithm, in this case, is extremely efficient. It's almost immediately goes out of this local minima. Yeah, now at very high temperature, of course, this algorithm is not that efficient. So let's go to high temperature. And then you see that actually Metropolis does pretty good job at high temperature, while Wolff is kind of relatively inefficient because there are almost no clusters yet. So Wolff is good at the transition, where of course the physics is most interesting, and below the transition. Now, the reason that I'm showing that I'm explaining all this is because I want to show you, or well, I'm not going to derive anything, but I'm going to show you what this Wolff algorithm actually does. So here's the description. So Wolff's algorithm. So what we do is the following. Instead of flipping a single spin in Metropolis that we implemented just now, we are flipping here an entire cluster. Now, what's the cluster? The cluster is almost domain wall, but not quite. So let me explain how we create a cluster in the Wolf's algorithm. So the spin I is selected at random. So this is the same as what we've done up to now. And then we try to we actually start to create a cluster out of this single spin. So we look at all nearest neighbors of this spin I, and we call this nearest neighbors J. So J are nearest neighbors of the spin, and these nearest neighbors are added to the cluster with probability 1 minus e to the minus 2 beta j. Okay, so this is actually the crucial point of the algorithm. We do not we accept them at zero temperature. At zero temperature, when beta is very, very large, we always accept all the spins that point in the same direction. So basically, at zero temperature, the cluster is the same as domain. But at finite temperature, the cluster is not the same as domain. So the cluster is smaller than domain. So we add to the cluster with probability this e to the minus 2 beta j, provided that spin I and j are parallel and the bond between I and j has not been considered before. So in other words, we go to a spin to some lattice site I, we look at the left, right, up and down, and we check whether these spins are pointing in the same direction. If they do, we most likely add them to the same cluster. Most likely means probability with this 1 e to the minus 2 beta j. Not always, but most likely we add them. And then, yeah, so the point is that once we have those extra spins in our cluster, then we have to do things recursively. So what means is that each spin j that is added to the cluster is also placed on the stack. So just to remember where we are right now, once all neighbors of I have been considered for inclusion in the cluster, a spin is retrieved from the stack and all its neighbors are considered in turn for inclusion in the cluster as well, following step 2. So you see this basically, well, the stack is basically just the way to remember which spins were visited in previous configuration and have not been considered before. Okay, so yeah, so just so that we grow this cluster, with time. So then the step 2 and 3 are repeated iteratively until the stack is empty. So why does the stack become empty at some point? Well, imagine that this is our domain, and then if we let's say that we are considering zero temperature, then when we look at the neighbor of let's say spin on the boundary, and we already selected all the spins which are pointing in the same direction, then the only one that we still didn't consider is the one here, but this one here points in the opposite direction. Therefore, we are not going to add it. So when we go around, we try all configurations. We see that basically all the spins that we can still consider have the opposite or the wrong spin configuration. Therefore, we don't have anything to add to the stack, and the stack is empty. So we are done. So in other words, once we exhausted the entire domain, we see that the stack is empty. Okay, so now with repeating these two and three steps, we finally mapped out the cluster. And once we did this, once the cluster has been completed, all spins that belong to the cluster are inverted. So you flip all the spins at the same time, and we are done. Okay, so you see, this algorithm is something that is so simple that you could easily modify the existing code to do the Wolf algorithm. And what we should see is that this algorithm should have way shorter time, would need shorter time to equilibrate or to calculate specific heat. Yeah, so now if you look at this algorithm, at this plot again, you will recognize this algorithm. Basically, what happens at each step is that we map out the more or less the domain, and then we flip the entire domain. Therefore, the color sometimes changes from completely black to completely white. Okay, so now, unfortunately, I'm not going to prove to you that this algorithm described here leads to the Boltzmann distribution in the Markov chain, because in order for the simulation to produce proper thermodynamics or proper simulation, we need to make sure that the Metropolis chain has the Poisson distribution. This is slightly non-trivial because it turns out that it requires one to map this model to some other model, which is a model of these clusters, and then one can show that actually this algorithm does produce exactly the same Boltzmann distribution, and we can then measure thermodynamic quantities with it. Now, I just wanted to make you aware of these cluster updates, which are efficient and improve the algorithm substantially, but we are not going to actually implement, and I didn't actually prove that this is the right thing to do. What we are going to do instead is we are going to calculate thermodynamic quantities with even more efficient algorithm, which is called Wang-Landau algorithm. Yeah, but before I go there, is there any question from the audience about these algorithms? Do you have any question? Anybody? No question? Anything's clear? Okay, then let me share the screen again. Yeah, so the algorithm that I want to explain now is way more efficient to calculate thermodynamic quantities. Unfortunately, there are the quantities which are not thermodynamics cannot be calculated with this, but we can calculate specific heat, we can calculate total energy. Yeah, what else? Can we calculate? Yeah, do we calculate magnetization? I guess no. So we can only calculate quantities which can be calculated with the density of states which correspond to certain energy. So at the end of the day, what this algorithm does is it calculates density of states, GOV. So this is many body density of states which correspond to particular energy E. Okay, so this is more or less entropy. Okay, kind of entropy. It's a proportional to entropy of the system. So how do you see this? I mean, if you had a thermodynamics course, you remember that entropy is kind of logarithm of all possible states that you have. Okay, so this is logarithm of G is basically like all possible states that you can have. So in some sense, what we are plotting here is almost entropy of the system. And we know that if you have entropy, then from this you can calculate all thermodynamic quantities, isn't it? Very precisely. And this particular simulation shows you specific heat for 256 and 256 simulation. So this actually corresponds to the same lattice size that I think we are simulating here, 256 and 256, as far as I remember. And you see that for this large lattice size, a specific heat is very, very, very sharp. And you see how precise this how precise curve we get. So from such a curve, we can definitely calculate the critical exponents. So the critical exponents, of course, have to do with how the specific heat diverges. So specific heat goes as T minus Tc to the power of I forgot what it's called, delta, one of the critical exponents, isn't it? Delta is critical exponent. Yeah, I mean, in our Metropolis, this delta we will not be able to calculate. We will not be able to see it because we don't have sufficient precision. But of course, with Wang-Landau, that is not hard because, well, we can, for example, plot this curve from here up in log-log plot, and we will see in log-log plot very clearly what's the slope. Okay, and that will give you the critical exponent. Now, what is the Wang-Landau algorithm? Well, it's kind of quite different in philosophy. So it's not a small modification of the cluster, such as cluster algorithms, but it's really different in philosophy. So it's very useful for studying the phase transition phenomena because it does not suffer from critical slowing down and gives direct access to the thermodynamic potential and its derivatives. So critical slowing down. So, I mean, cluster algorithms also don't suffer from critical slowing down, but Wang-Landau is probably even more efficient than cluster updates. Now, how does it work? The first approximation, what we are trying to do here is, instead of thinking of configurations X, X, you remember, was configuration, we are thinking only of energies, because somehow we say that, you know what, there are so many states that have the same energy. So why do we want to visit the same energy many times, but all the configurations that have the same energy contribute exactly the same to the thermodynamic potential or any thermodynamic quantity? Okay, so let's say that you want to calculate a specific heat, or, well, let's say just energy, average energy. So we want to calculate some energy, some average quantity A, and we calculate it by probability of X, which is Boltzmann, E to the minus X over T, divided by Z times A of X, isn't that? So that's what we were doing right now. Okay, and now we realize that there are lots of these X's that have exactly the same energy, and therefore, let's say that this quantity A depends only on the energy, not on the not directly on a configuration, but only depends on energy. So once more, this simulation is possible only if the quantity that we're interested in, thermodynamic quantity, is A of X, is basically depends only on A of X that depends on, well, basically this is not the best way to write. It depends only on energy. So that's the question, isn't it? So thermodynamic quantities have this property, so that basically they don't depend on the details of configuration, but only on the energy. And so what we realize that the number of energies is relatively small compared to the number of 4 possible configurations. And if we could just enumerate how many energies have the same configuration X, we could do calculation much easier. So imagine that instead of doing this, you would sum over all possible configurations that have the same energy, okay, and of P of X, of course. Then you would see that basically this is the number of the many-body states at this energy divided by Z to the minus E to the minus E over T, okay? And then once you have this number of many-body states, then we know that the average quantity that depends only on energy is basically just is basically this quantity A times number of many-body states divided by Z times E to the minus E over T. So in other words, once you have the many-body density of states, you can calculate thermodynamic quantities completely trivially by just many-body density of states times the Boltzmann factor. That's it. or Z is basically just number of many-body states times E to the minus E over T. Okay, so the question is, of course, how many states do we have at each particular energy? Once we know that, we're basically done. Okay, so in order to make this kind of more obvious to you, I want to do the calculation for the smallest possible cluster, which is 2 by 2. Now here, unfortunately, when I was typing this, I was considering here the sign to be plus. In the ferromagnetic Ising model, the sign is minus. Now I kind of switched here from the antiferromagnet to, no, from a ferromagnet to antiferromagnetic Ising model. For this consideration here, at least for enumerating the states, it doesn't matter. But I realized later on that it would be more convenient to have a minus here. But I don't want to translate. I don't want to change this right now. So anyway, the energy is, as we said before, is basically J S I S J, sum of all neighbors I and J. Okay. So now, how many energies do we have for this 2 by 2 or 4-side cluster? Well, I will argue here that we have only 3 different energies, either plus 4J, minus 4J, or 0. There are only 3 different energies. How many configurations we have? Well, that's easy. So each spin can be up or down. So we have 2 to the power of 4, isn't it? So we have 16. We have 16 states, and we have only 3 energies. So in general, we can figure out that number of energies that you can have is of the order of n. So we will actually enumerate them. So there are not so many energies. They're only of the order of n energies, where n is the number of lattice sites, while the number of many-body states is exactly 2 to the power of n. So the number of many-body states grows exponentially with the lattice size, while the number of energies goes linearly with lattice size, and that's a huge difference. Okay, so therefore it means that every energy is very, very, very heavily degenerate, and therefore the many-body density of states at in this small cluster basically will be like this, 2, 2, and 12. But then eventually, when we have a large cluster, we will see that basically this density of states looks like that, and it's very, very large in a center, exponentially large. Okay, so let me first explain how did I get this many-body density of state GOV. So we consider all possible states. So there is this ferromagnetic ground state. Okay, so this one is ferromagnetic ground state when all spins are up, and we know that this has energy 4J. Why? Because there are 1, 2, 3, 4 links, isn't it? There are 4 links, and each link contributes J, so we have the energy is 4J. Then when all the spins are down, of course, this energy has the same. This has the same energy. It's also 4J. Okay, so therefore, and that's all. So there are no other states, no other configurations that have energy 4J. So those correspond to this. Okay, so these 2 states, which are ferromagnetic ground state, are in this case so this state is twice degenerate. So the energy plus 4J is twice degenerate. So the many-body density states has value 2 here. Then the opposite, when we have this so-called antiferromagnetic configuration, where the 2 spins point up and 2 spins point down, so this is the so-called nail state, it turns out that there are then, well, first the energy is minus 4J. So how do you see that? Well, you look at the neighbor of each spin, and you see that all neighbors point in exactly opposite direction. Therefore, the system is antiferromagnetic. So this one has all the neighbors opposite. This one has all the neighbors opposite, all the neighbors opposite, all the neighbors opposite. And if that's the case, then energy, at least in this for this Hamiltonian, is minus 4J. Okay. Now, how do we know that it's doubly degenerate? Well, because on this lattice side, for example, I selected now that the spin is up, but I could also equally well select the spin on this side to be down. And once I select that, then all other spins are determined. So we know that there are two configurations like that. Okay, so now we see immediately that this many-body dense states is kind of symmetric. So there are two configurations which are antiferromagnetic-like and two which are ferromagnetic-like. So therefore, this minus sign that I forgot here to consider antiferromagnet, it doesn't matter because the many-body dense states for antiferromagnetic and ferromagnetic Ising model look the same. Now, what about the rest of the states? Well, the rest of the states typically look like that. So we have one spin which is opposite to the rest of the spins. Okay, so one spin is down, the rest are up. So in this case, we have what happens? So we have, for example, this guy has all links to be opposite, but this guy has all links to be equal. So therefore, this contributes -2, no, -2, I guess, and this one contributes +2, so the energy is 0. Now, similar here, you can convince yourself that the energy is 0, and here you can convince the energy is 0. So all other configurations have energy 0, and this one turns out to be 4 times degenerate, 4 times degenerate, 4 times degenerate. Why? Because, for example, only one spin is down, but you can place it in any possible lattice site. So therefore, the degeneracy is 4. So this state means basically 2 down and 2 up, but in this way. So I guess you can either select this bond to be ferromagnetic, you can select this bond to be ferromagnetic, or you can select this bond to be ferromagnetic. So there are 4 configurations like that. So now you understand that the many-body density states for this particular 2x2 antiferromagnetic Heisenberg model looks like that. So we have only 3 states. And once we know this GUV, we can, of course, calculate every thermodynamic quantity very, very quickly. So again, let me emphasize that the number of states is 2 to the power of 4, which is 16, which is 12 plus 2 plus 2, isn't it? It's 16. But we have only 3 energies. Okay. Now, next step in this algorithm is to enumerate all the energies. So if we don't know what energies are possible, then we actually cannot run Vanglando algorithm. But in Ising model, we know which energies are possible. Okay, so these are the energies. Yeah. So how do we calculate them? Well, we just need to look at our configuration. Now, currently, I will switch to, I'm very sorry, I'm going to switch to ferromagnetic Ising model. So I'm put a minus again, back, like we did before, like we had before, minus J, SISJ. And then we can see that, let's say that, that we are in the ground state, where all the spins point in the same direction, and we are now trying to flip one spin. Let's say that this spin that we try to flip is this blue one. Okay, so all the spins point in the same direction currently, and we're trying to flip one spin. So what is the energy cost to flip this single spin when we're in the ground state? Well, we look at how many bonds we're gonna break. So 1, 2, 3, 4 bonds. We could also just look at the Weiss field. Weiss field in this case is 1, 2, 3, 4 plus 4. Okay, and the spin is the same as the Weiss field, so therefore the delta E is supposed to be 4J. Or in other words, we just look at how many bonds we're going to break. This is number 4 bonds. So the energy cost in this case is 4J. Okay. However, once at least one spin points down, then in order to flip the second spin, which is nearby, then the energy cost to flip this spin is going to be what? It's going to be, so this will contribute -1, this will contribute +1, +1, +1, so it's going to be 3 minus 1 is 2. So the energy to flip, for example, this spin is going to be 2J. Okay, the energy for flip, yeah. So sometimes when you have, for example, 2 down and 1 up, well, yeah, if we have a spin which has 2 in down direction and 2 in up direction, then we know that the energy change is going to be 0. So in other words, generically, the energy change can be either 0, can be 2J, or can be 4J. And these are all. No other possibility, isn't it? So the energy change, we discussed this even before, that the energy change can only be this 0, plus minus J, and plus minus 4J. Okay. Now, from this, it's kind of obvious to see that the steps in total energy is gonna go in units of 2J. Okay, so the energy levels will be kind of uniform from maximum to minimum. Maximum is very easy to calculate, minimum is very easy to calculate, and the steps are supposed to be 2J. Now, the only exception to that rule is the first excited state out of the ground state. So it turns out it has a little gap. Why? Well, we just explained this, that when we try to flip the very first spin, we always need to pay the price at least 4J. So when all the spins point in the same direction and we try to flip the first spin out of the ground state, then we've always paid the price 4J. While afterwards, when one spin is already flipped, we could pay the smaller price 2J, and then later on also price 0, which basically means that we have large degeneracy. But so now that I explained you this, it's kind of obvious that the energies have this configuration. So in other words, the change of energy is of the order of 2. Well, it's 2J. So we have 2J n minus 4, 2J n minus 6, 2J n minus 8. Yeah, so there seems to factor of 2 here. Is this true? So except the first step is bigger. So the first step from the ground state, the change is for a change is 4, and then later on the change is only 2. Now I do see that here the energies are there is a difference here by factor of 2. I think this has to be twice as big, it looks like. So basically the change here is actually should be 8J, and the change here should be 4J, because the first step is actually 8, and next step is 4, and next step is 4, and 4, and so on. Yeah. So I think that I have a factor of 2 missing here. Like this. So this should be right, I think. Yeah, so the important point is that these are all the energies that we can visit in our simulation. So it starts with the ground state, which we figured out last time, that it has energy minus 2J the numbers of lattice sites. So n here is the number of all lattice sites. Now, how do we check this energy? We said before that each spin has 4 neighbors, so it's 4 times J. Then naively we would say that it's 4 times J times the number of lattice sites, but each link then is counted twice, so we need to divide by 2, and we get 2Jn. So this is the antiferromagnetic ground state. The ferromagnetic ground state is going to be opposite, and then the jumps. The first jump is for 8J, and next jump is then for 4J. Yeah, so these are all possible energies that we can have. And once more, I want to emphasize that the number of states, however, is much, much bigger, is of the order of 2 to the power of n, exponentially many. Now, once more, I want to show you now how to so the classical Monte Carlo simulation generates canonical distribution at a given temperature, which has probability POV is number of the states at this energy times e to the minus e over t. So again, how do you see that? Because our distribution for the state, generic state P of x has to be Boltzmann, isn't that? E to the minus Ex over T. But if we look at the probability for the energy E, isn't it? Then this is equivalent to summing over all configurations that have the same energy of P of x, which is basically this G of E to the minus U over T divided by Z. So it's proportional. Probability for energy is proportional to the number of density of states times E to the minus U over T. Okay. So the idea of Vanglando is to estimate the many-body density of states G of E directly. Okay. So the temperature is not required for a simulation, and by analyzing density of states, one can study thermodynamics at any temperature. So basically, this density of state G of E, as we saw here in this simulation, here when we consider density of states, this is independent of temperature. This is density of many body states for a particular model, has nothing to do with temperature. So we can calculate this quantity without considering temperature. But once we have the many body density of states, then we can calculate any quantity out of it. I mean, one way is, of course, to calculate it the way I sketched here, but there is an alternative way, which is maybe more convenient, is to recognize that Z is basically just the number of many body states times E to the minus E over T. Okay, so G of E, so Z is basically just number of many body states times E to the minus E over T, Z partition function. Okay, so therefore we know that free energy is minus K Boltzmann times T log Z. This comes from knowing thermodynamics. Therefore, the free energy is going to be K Boltzmann times T log G of E to the minus E over T. Of course, the alternative is to calculate any quantity that depends only on energy, and then multiply it with this way, G of E divided by C E to the minus E over T. Of course, we're going to get the same result. So my point is that once we have many body density of states, G of E, we can calculate free energy or entropy of any thermodynamic quantity simply from G of E for any temperature. Now, of course, the trouble is that we need to calculate density of states where the number of all possible states is exponentially large, is of the order of 2 to the power of n. So let's say a naive way would be to write a loop over all 2 to the power of n states and just calculate energy for every state well, just count them, enumerate them, doesn't it? So that's if you want to do Wang-Landau in a more primitive way, it wouldn't be called Wang-Landau, but if you want to calculate density of many body states, you would just loop over all 2 to the power of n many body states, and you would calculate energy of every state and would see how many states have the same energy. You would see the degeneracy. Okay, so once you have that, then you can calculate all thermodynamic quantities from knowing that. However, when number of lattice is large, there is no way we could actually loop through all the many body states. There are just too many. Our 20-site lattice problem has 2 to the power of 20 possible states, which is kind of way too large that our Jupiter would survive. So therefore, we are not going to do that in this brute force way. So we are going to follow then Wang-Landau algorithm, which uses Monte Carlo to visit configurations in particular ways, so that calculates many body density of states. So what do we do? Well, in Wang-Landau algorithm, the random walk in energy space is performed, and probability to visit a state with energy E is taken to be 1 over the number of many body states. So the important point is here that we are doing random walk in energy space. You see, we are not doing random walk in configuration space. We are not visiting X, or basically configuration, like we did in previous Metropolis, but we are visiting energies. And we know that there are not so many energies at the end of the day. We said that there's a relatively small number of energies. So, probability to visit a state is then being set to, so that's the idea, set probability to accept a step as 1 over the number of many-body states. But we don't know the number of many-body states yet, doesn't it? Well, if we don't know something, then we can do self-consistently, doesn't it? So we first guess some number of many-body states. We do the random walk. We check how the many-body states would look like, and then we update the number of many-body states, similar to what we were doing in Vega's algorithm. So here we kind of do it self-consistently. We select some guess for this quantity. We do some random walk, we update, and so on and so forth. Now, this is a little bit tricky. We are going to do something which we're going to look at the histogram. So in order to say that we can kind of we can know that we have successfully performed random walk through relevant configurations, for all the relevant configurations, how can we say that? How can we figure out that? How can we say that we've seen most of important states or most of important energies? Well, this we will judge when our histogram is flat. So what is histogram? Well, histogram is how many times did we visit the state with particular energy. So we are going to run the Monte Carlo simulation, this time in the space of energies, and then we're going to see how often did we visit certain energy E, and we're going to say, well, if our probability to visit a state is 1 over the number of density of states, but with the degeneracy is G of V, then we know that each state is supposed to be visited with the constant, the histogram should be flat. So once more, so this algorithm selects that the probability to visit certain energy is 1 over the number of density of states, but the degeneracy of each state is G of V. So therefore, G of V times P of V, which is 1 over G of V, has to be 1. But this is proportionality. So it means that histogram has to be constant. Okay. So if we run, so what this thing says is that if we run our simulation for an infinite amount of time, we should see that the histogram is flat. Okay. Why? Again, the histogram will be flat once we simulate this for a very long time, is because we are visiting configuration with 1 over the number of many-body states. On the other hand, we know that the degeneracy of each energy is G of V, so therefore the probability that we're going to visit a state with particular energy should be roughly constant, or should be constant. Okay, so let me explain this on this particular example. So if we select the probability that the state 0 should be visited 6 times less probable than the two excited states, so this antiferromagnetic state and ferromagnetic state, if I select that this state 0 is supposed to be visited 6 times less with less probability than these two, so let's say P probability for state 4j and minus 4j is, let's say, some small p, but probability for this state is 1/6 of that. So then, however, I also know that this state is 6 times degenerate. So therefore, I know that the histogram is going to be flat, because I'm going to visit this probability the state with much less probability, but there are so many more states of that type. So therefore, the histogram will be flat. Okay. So is this kind of clear to everybody? What I tried to explain? Did you understand? Anybody? Or did I lose you? Still around? Anybody? Okay, so the important point is that we want to simulate this Wang-Landau as long as we don't see that the histogram is more or less flat. Once the histogram is flat, we know that we are basically simulating long enough. Okay, so but let me go now more into details of the algorithm. Yeah, well, first let me run this. Let me read this. So in our example above, a simple random walk would visit a state with energy 0 6 times more often than the other two states, since there are 6 times more states at E0. If we assign probability for the state minus 4j to be proportional to 1/2, probability for the state 0 1/12, and probability for the one at 4j to be 1/2, we will visit all three states on average the same number of times. Hence, the histogram is flat. So now again, I explained this, what means histogram is flat for this particular problem. If we assign again properly the probabilities, and we are doing random walk in phase space, we could get the histogram to be flat for this particular problem. Okay, so if you understood now the basic idea of Vanglando algorithm, you will recognize why this algorithm actually produces what we want. So the algorithm is the following. The transition probability to go from certain energy E1 to E2 has to be 1 over the number of many-body states. So basically, according to, so if P is proportional to 1 over G of E, isn't it? So then P of E, of course. Then we know that Metropolis, so Metropolis requires that transition probability to go from E1 to E2 has to be 1 over the new G of E, but of course needs to be the ratio between the current divided by the new one, isn't it? So this is how Metropolis gets the transition probability if we know the probability for a certain state. Basically, in previous lectures, I think we call this rho. So if rho is 1 over G of V, then, well, provided that the trial step probability is symmetric, so we remove here trial step probability, we said this is symmetric. So if the trial step probability is symmetric, then we know that the transition probability from a state with energy E to another state with energy E is just the ratio of the two rows, isn't it? Okay, so therefore this the acceptance step probability is going to be many body density of states of the old configuration divided by the many body states of the new configuration, or it could be 1 if the ratio is bigger than 1. Okay, so we always accept move with smaller density of states, but we often reject moves which would bring us to the state with high density of states. So that's what this thing says. So you see, if the many body density of states, if the ratio of the two is bigger than 1, we always take the step. If the ratio is smaller than 1, we sometimes take the step, sometimes don't. Okay, so therefore, when we move to the density of states which have smaller g means that this is going to be bigger than 1, we will definitely accept the step. But if the new many body density of states is the one that has bigger g, then the ratio is less than 1, and we sometimes accept the step, sometimes we reject the step, isn't it? Okay, So that's the basic algorithm. This is what Wang-Landau postulated. This is the postulation of the Wang-Landau algorithm, is that we are going to simulate, rather than accepting the step with Boltzmann distribution, we're going to accept the step with this in this way. Otherwise, we're going to run the same Metropolis algorithm. Okay, then we're going to start with all density of states. We're going to set to 1 at the beginning, because we don't know enough about the system, and then we're going to try to estimate the number of many-body density of states self-consistently. Okay, now how do we do this self-consistently? Well, unfortunately, time is 6:20, and I will not be able to explain this. I would like to explain this on Wednesday when you return. Is this okay? So do you have any urgent question?